All right. So we're going to begin chapter 8, and this deals with what we call hypothesis testing, statistical tests to decide if we should reject or accept an hypothesis. Excuse me. So let's get into it. In chapter 7, what we did is we constructed an interval around a sample statistic that would predict, roughly where the population parameter was located. And so what we're going to do is kind of similar to that, but what we're going to do is look at what's the likelihood we would fall at extreme value if the population parameter was where we think it is. And if it is, if it's very unlikely we would be at that extreme value, then we're going to look at rejecting what we think the population parameter is. That's where this is going to go. All right. So yeah, we're going to see if there's been a change in that population parameter. When we're testing, we're going to create two hypotheses. The first one is what we're going to call the null hypothesis. And this is that the change has not occurred that we're looking at. Now, that's a little misleading. There could be a change, but it could be in the wrong direction. But we're specifically going to be saying, we want things to change in a specific way, or maybe they just change somehow. The key here is the null hypothesis is always going to include an equals. It's always going to be the default, the status quo choice. And then the alternative is going to be that whatever kind of outcome we're looking for, whether it's a good outcome or a bad outcome, that has happened, that change has occurred that we're looking at. All right. We're going to look at the difference between one-tailed and two-tailed tests. So in a two-tailed test, you're going to look at, we think the mean, let's say, that's the population parameter we're looking at, is here. And the two-tailed test says, well, it could be really lower than that or higher than that. It could be on either end. So this end or this end. We're not making a claim one way or the other, which end we think it should go to. We're just saying it's not where we think it is, in the middle. That's the two-tailed test. So we were going to consider both of those possibilities. What this means for us is we're actually going to split our chance of being wrong in half. So we're putting half of that chance on one end and half that chance on the other. It's going to make it harder to make that prediction. All right, a test can be one-tailed in two ways. You can have what we call a left-hand test, left-tailed test. The alternative is that the population parameter went down. It's less than what we think it should be, the status quo value. Or the right tail, that it went higher. It's greater than that status quo. And what that's going to mean is we're going to give ourselves a certain level of, I'm willing to be wrong by this percent. I'm willing to be 5% chance I would be wrong. We're going to put it all on one end. We're not going to split that 5% into both ends. We're just going to say it's all on that end there. That's going to give us a little bit more wiggle room to reject the null hypothesis in that case. And we'll see how this all works out. All right, so when we construct it, let's say we had this. A car company redesigns an engine and claims that the average miles per gallon will increase. And so we want to construct our null hypothesis, that's the H sub 0, and our alternative, that's the H sub 1. So what we're going to claim is in the null well, sometimes it's actually easier to figure out the alternative. So I'm going to start with that the average is going to be greater than, let's see, what notation are we using here? So the average is going to be greater than the initial thing. And then the null hypothesis would be that this new value for the average is actually less than It's actually less than or equal to the initial one. So they're claiming we redesigned the engine, and now you're getting better average miles per gallon, and that's their claim. That's the alternative claim. And the null hypothesis would be no, it's not better. In fact, it could be even be worse, but it's not better. That's how we would construct that. And the null hypothesis, this null hypothesis always has the equal to. Now, you could instead say this. You could say the alternative would be that it's better, and the null would be that it's equal to. But to me, that doesn't really make sense. You have to account for the possibility that it could even be worse. So that would go in this situation. But this is a one-tailed test. One-tailed test. And this is the right tail, right? Because we're going bigger. We're going bigger. All right, example 2. A school district believes that the probability of students passing a standardized test is different between 2 high schools. Now, it's not claiming one's better than the other. They're just saying we think that they're not the same. And, you know, this might be a preliminary situation. So they're going to say our null hypothesis is that 1 does not equal, or sorry, mess that up. That the null hypothesis would be that they are the same. That they are the same. And the alternative would be that they're different. That the average of the first one and the average of the second one are different. And I just messed those up. Those should be P's, because we're talking about probabilities. Sorry. I'm a little rusty. So we're getting there. All right, those should be P's. So the null hypothesis would be that they are the same. The alternative hypothesis would be that they're not the same. And this would be a two-tailed test, because we're not claiming one way or the other, which one's better, which one's worse. We're just saying we think that they're just not identical, that their averages are different. All right, so let's talk about some concerns we have and some possible outcomes when you do hypothesis testing. So on the left-hand side of this table, we have whether the null hypothesis, remember that's the default situation, things haven't changed, is true or not. And on the top of this table, we have the decision whether we should reject the null hypothesis or not to reject the null hypothesis. So in the first box here, we say, okay, the null hypothesis is true, and we don't reject it. You know, we do our research and we say there's not enough information to clearly reject the null hypothesis. Well, that ends up being the correct choice. The null hypothesis was true, that things hadn't changed, and we didn't say they did. So that's great. That would be a correct decision. Let's look at the fourth box here. The null hypothesis is false, and we have enough information that we can say, let's reject that null hypothesis. That things have changed. Things have changed in the way we had predicted they would change. And we say, you know, that means the null hypothesis no longer is true. And we say it's not true, and we made the correct decision. Awesome. That's what we want to happen. There's also 2 other possibilities, and that's these other 2 locations. So you could have the null hypothesis is true, but based on, like, you know, because we know samples are not 100% representative, you might do a sample and you think it's wrong. You think things have got, you know, like, think about that engine situation. You thought the engine was better, you know, and you say, you know, we need to switch all our cars to this new, more fuel efficient engine. That would be this type of error, this type 1 error, that you're rejecting the null hypothesis. You're saying things changed, and maybe they changed in a good way, and so we're gonna reject that. We don't want that to happen. Okay, we're gonna reject the null hypothesis. We don't want to stay with things as they are. Reject it. Let's change stuff. That's a type 1 error. A type 2 error is down here. This is when the null hypothesis is false. Like, you think your engine's better. You do a sample, do some research, and you find out, like, I can't say for certain it's better. I think it's better, but I can't say for certain. And they say, okay, well, we're not going to change the engines. We're not going to reject the null hypothesis. We're not going to say this engine is actually better. We're just going to say, we don't know if it's better, so we're not going to change things. Now, like I said, 2 of the 4 are great. We want that to happen when we are correct. The other 2 are errors. One of those errors is actually worse for most situations than the other one. And that is a type 1 error is more significant. Think about that engine situation. Let's say you do a study and you think this brand new engine is more fuel efficient, but it's not. It's not really more fuel. In fact, it might even be worse. But just because of the situation you looked at, maybe it was a really smooth road, some time of year, some other factors got involved, and it ended up looking like it was better. And you go, okay, let's redesign our entire assembly line. Take out the machines we had, put in new machines. And so think about all this capital investment, all this investing in the company that would have to make that kind of change. And then later on, the company gets sued because they claimed it was a better engine, and it turned out like other people did research and found out it wasn't a better engine. In fact, it was a worse engine. And so they bought the car thinking they would get more fuel efficiency, and they didn't. So that is a horrible outcome. That's why type 1 is the worst of those 2. Type 2 says, we're just going to keep doing things how we're doing it. We're just going to status quo. We're just going to keep going. And a type 2 error happens. It means like, well, maybe we're not making more money than we were, but we're not making less, right? We haven't made a bad mistake. Maybe we're making a mistake of opportunity. We're not taking an opportunity that is available to us. So we're losing out on that, but we're not making the situation worse. We're just keeping it the same. That's a type 2 error. Keep things the same. Lose out on maybe an opportunity, but keep things the same. Type 1 error is you take a chance and it actually blows up in your face. That it doesn't work well, So we want to control for that type 1 error. We're not too worried about the type 2 error. We're okay with that. We're worried about the type 1 error. So again, it's just rejecting the null hypothesis. So the probability of making a type 1 error is what we're going to call the level of significance. It's going to be, we're going to label that alpha, lowercase alpha. The p-value is the probability that a sample statistic would take a value equal to or more extreme than the observed test value. And for the two-tailed test, we're going to double that. So let me kind of translate what this says. I go to my, I'm the head of the engineering department. We design the new engine. I go to the CEO of the company or whatever, we say, hey, we got this new engine. We want to put it in production. We've done some testing. We think it's better. And the CEO says, okay, we don't want to lose money on this. How sure are you? And they're like, well, we're pretty sure. And he's like, look, I'm willing to make, there to be a 5% chance you could be wrong. 5% chance that you could be wrong. So 95% chance you're right. But I'm willing to accept a 5% level of risk. That's what the level of significance is what's the probability you're willing to accept risk level of? Well, 0, no. You're not going to have a 0%, because that means you're just like, I don't accept any risk. You might as well just say we're never going to innovate. You have to accept some level of risk, and that's what the alpha is. Maybe it's only 1%. Maybe you're only willing to 1% level of risk, but this is a risk amount. And the probability, the p-value here is, well, let's say the stuff is working how it's supposed to be working, like we think it has worked in the past. What's the chance that your random sample that you took would end up in that extreme value? So let's say I say the risk of getting a better engine, or being wrong about the engine, is 5%. I'm willing to take a 5% level of risk. and we do a study and we say, well, there's a 7% chance that I would end up that thing. And I'm like, well, we're not going to reject in that case. So that's more than my 5%. But let's say we end up on the extreme edge, so let's say we're doing a one-tail test, okay? And we do a study and we find, there's like a 5% chance we would end up here. That's my level of risk. Now we actually do the study and I find out my mean is actually more like has a probability value of 2%. And so they would say, well, that's smaller than my level of risk. I think it is better. I'm willing to take that chance that you would get 2% or higher, just in a normal, just lucky research thing, lucky sample. The chance you would get that far out is only 2% or high, that value or higher. It's only 2%. Well, that's a much lower than the 5% I set for. So we're willing to make that change because it is really unlikely that you got out there. Now, let's say you did the research and instead you got a value over here and it came out to be, from there higher, it came out to be 7%. Well, no, it's got to be, if my alpha is 5%, I'm like, that's more than my alpha. You need to get more extreme. It's not extreme enough. It's not extreme enough. It's got to be like less than 5% for me to make that assumption. So that's kind of how this is going to work out. That's kind of how this is going to work out. So we're going to reject the null hypothesis if our p-value is less than or equal to our alpha, our level of significance. We're not going to reject it if our p-value is greater than our alpha. It's greater than our alpha. Okay. So if it's more than, we're not extreme enough yet. Like there's still 7% chance you would land out there naturally. That's not where I set the alpha value. So we're not ready to transition. Remember, we're really trying to control that for that type 1 error. We really don't want to change things unless we are very confident it's actually going to create the change we want it to happen. All right, so we're going to determine the p-value and we're going to find the test statistic. We'll assume that we're looking at a normal population and that we know the sigma. So again, we know the sigma. That means we're working with z values. That's a big tie there. We're working with z values. Sigma and the normal distribution, we're working with z values. So to calculate this test statistic, we're going to take our sample mean minus our population mean and divide it by this standard of error, this sigma divided by the square root of it. All right, and that's just moving the formula around a little bit. But again, you might, we probably just want to do this with sigma over the square root of n and just calculate that and then divide that by there. Okay. This mu is from the null hypothesis. That's the default value. That's the status quo value. Okay, so the mean comes from the status quo value, the default hypothesis, the null hypothesis. Okay, so let's look at page 451, number 20. 451, number 20. Okay. So Gentle Ben is a Morgan horse at the Colorado Dude Ranch. Over the past 8 weeks, a veterinarian took the following glucose readings from the horse and has a list of those. Let the sample mean is this, 93.8. Let X be a random variable representing the glucose readings. We may assume that it's normal. And from past experience, we know sigma is 12.5. The mean glucose for a horse should be 85. Right, so this is our predicted level that it should have. Does the data indicate that Gentle Ben has an overall average glucose level higher than 85? Use alpha of 0.05. Okay, so here we go. What we're going to do, We're going to calculate our test statistic. So Z is going to equal X bar minus the mean over sigma square root of n. So we got a value of 93.8 minus our predicted value. And then our sigma is 12.5 over the square root of 8. Right? We're going to divide that out. I also need to do the null hypothesis and set up my two hypotheses. So I'm going to do that, but I wanted to do this calculation before I forgot the formula. Divide by 5 by the square root of 8. Oops. So this looks like about 1.99. We'll come back to that in a second. All right. So let's set up our hypothesis, our null hypothesis and our alternative hypothesis. So the question is asking us, does it indicate that the horse has an overall glucose higher? Higher, that's going to be the alternative. That the average level is greater than 85. And our null hypothesis is going to be that the average value is less than or equal to 85. Okay, that's going to be our null hypothesis. Now you can look at it and see, well, it's obviously not going to be less than. But the question is it so far up that with this alpha level, with this level of significance, that we would reject the null hypothesis, that we reject that he does have a higher blood level. Okay, so we're going to use our Z value. And this is a one-tail test. So this is what's happening here on the graph. On the graph, you have your mean, 85, which corresponds to a Z of 0, right? And we're going to go up here to 1.99. And we're going to figure out what's the probability we would land in that area. What's this probability? Probability that Z would be greater than or equal to 1.99. And what the alpha, what the level of significance is saying is if you have a more than 5% chance of landing up there, then we're gonna say he's okay. He's got the same blood as the other horses. It just, maybe he had a lot of apples or sugar cubes the last few days. But normally he's fine. If it ends up being smaller than 5% chance or equal to 5%, then we're gonna say no, his blood glucose level is higher. His blood glucose than a normal horse. All right, so let's go to our Z tables. We're using our Z tables, and we're gonna figure this out. So remember the probability that Z is greater than or equal to 1.99. That's not how the table is set up. We're gonna have to do 1 minus the probability that Z is less than or equal to 1.99. So 1 minus, go to my Z table, 1.99. 0.9767. And this is a one-tailed test. So I'm going to figure that out. 1 minus 0.9767. 0.0233. So how does that compare to alpha? Well, that's less than my alpha value. What that tells me is I should reject the null hypothesis. I should say, how do we want to say this? We want to, does it indicate? It indicates that Gentle Ben glucose level on average is higher than 85. Okay, that's what we're going to reject that null hypothesis. We're going to reject that it's equal to 85 or higher, because the probability that we would land that far up is only about a little bit more than 2, not quite even 2.5, 2 1/3%. And we said if we would put a 5% level. This is, if you get 5% or more, or sorry, 5% or less chance you would end up that extreme, then no, we say something's different. And so, maybe they need to start looking at the horse and seeing what they can do to help, handle that level. Maybe it's a problem and they have to deal with it. All right, let's look at 24. 24 here. All right, so total blood level per body weight is important in medical research. For healthy adults, the red blood cell volume mean is given by this 28 milliliters per kilogram. If it's too low or too high, that can indicate a medical problem. So both too low or too high is a problem. All right. Suppose that Roger had these 7 blood and we got a mean of 32.7. And we assume that it's normal and has a standard deviation of 4.75. Does the data indicate that the red blood volume is different than the standard mean of 28 milligrams per kilogram? Use a 0.01 level of significance. So I'm going to go ahead and do the hypothesis first this time. So the null hypothesis would be that this person's blood level is this 28 milliliters per kilogram. So the null hypothesis would be that it's not. It's either too low or too high. Either way is bad. Either way is bad. Now, looking at the data, we see it's going to be above. But, when we went into this experiment, we would have said, well, it could be either way. So I don't know. All right, so let's figure out the Z value. And again, that's going to be the mean minus our predicted value, our predicted mean, our standard one. And then we're going to divide that by the standard deviation divided by the square root of the sample size. I get that. Again, that's that standard error value. So 32.7 minus 28 divided by 7. So it looks like this is about 2.62. And again, when we're using the Z table, we want to round it to 2 decimal places because that's how the Z table is set up. All right, so what's going on here? We're setting this at a 1% level of significance here. So we're saying if you end up extreme one way or the other, and if you were to double that, because we're counting both ends, and that when you after doubling it, you came out to be higher than 1%. Likelihood you would get extremely that far one way or the other, then we're going to reject the null hypothesis. All right, so what's the probability that Z, and again, we're going to be higher here, right? So Z is greater than or equal to 2.62. And we're going to have to subtract it, do the complement, because that's how the table's set up. 2.62. So 2.62.9956. Okay, 0, 0, 4, 4. Now, that's not what we're going to compare to alpha. Since this is a two-tailed test, we're going to multiply that by 2. Oops, I'm getting ahead of myself. Multiply it by 2. So 0.0088. Now the question is, how does that compare to alpha? And again, that is smaller than alpha. That's our alpha value. So we're going to reject the null hypothesis. So what does it say? Does the data indicate that Roger's blood volume is different? Yes, it indicates it is different. Different from this standard value of 28 milliliters per kilogram. Now we're not going to say it, we're going to make the claim that it's higher, even though that's what it looks like. We're just going to say it doesn't look like it is that value. And then you could do another study where you would look at, doing it, setting it up as a one-tailed test. As a one-tailed test. All we can say right now is it doesn't look like the blood, what's this? The blood volume per body weight measurement is what we would think it should be. So we're just rejecting the null hypothesis. Okay, so why don't you do for this assignment 3 through 11, 19, and 23. That's the entire assignment. And what we're doing, first thing you want to do, even though they don't always say write the hypothesis out, every time you do one of these problems, you want to write the null hypothesis and the alternative hypothesis. And the null hypothesis always includes the equal sign. Always includes the equal sign. It's the standard. It's the predicted outcome of, if things were totally normal, if things hadn't changed at all, that's the standard. That's the default. And then status quo, you would say. And then the alternative is that there is some kind of change from that status quo situation. All right, so that's our introduction. And as you can probably imagine, we're going to be doing this with the t-values, without sigma. That's coming up in the future sections, but we'll see you then.